Chapter 5, an introduction to solutions and aqueous reactions. And the quote here is from Karl Popper. Science may be described as the art of systematic oversimplification, the art of discerning what we may with advantage omit. So we need to talk about solution concentration. A lot of chemical reactants involve reactants that are dissolved in water. These are called aqueous solutions. If we have a homogeneous mixture of two substances, such as salt and water, that's going to be a solution. A solution is always homogeneous. In the solution, there are two parts, the solvent and the solute. There's different ways to define them, but generally the solvent is the one that there's more of. Yeah. Yeah, absolutely. Yeah, it's a little tangled up there. Actually, why don't you unplug it? Let me stick it down here.
Thank you.
Mm-hmm.
Sorry.
No problem. So the solvent is the one that there's more of. If there's water present, water is always the solvent. The solute is whatever is present in lesser amount. So if you have salt water, water is the solvent, salt is the solute. Salt is dissolved in the water. You can have more than one solute. You could mix sugar and salt in some water. It wouldn't taste very good, but you could do that. And the amount of the solute is variable. You can put a little bit or a lot. So it's not a compound, it's a mixture. The composition can vary. An aqueous solution is one where water is the solvent. So we can describe solutions qualitatively or quantitatively. Qualitative descriptions would be words like dilute and concentrated. A dilute solution is going to have relatively a small amount of solute compared to the amount of solvent, whereas a concentrated solution is going to have a large amount of solute. So here we have an illustration. This one is concentrated. There are more solute molecules dissolved in the same amount of solvent than over here. You could also think about frozen orange juice. You go to the grocery store and you buy a little can in the freezer. It's orange juice concentrate, right? Because they took a lot of the water out of it. It's got a lot of more orange goodness in it. And what you do to make it drinkable is you dilute it. You add more water. Of course, in chemistry, we are concerned a lot with the quantitative descriptions of concentration. And the one we use the most is called molarity. So molarity, and it's abbreviated with a capital M. Molarity is the amount of solute measured in moles divided by the volume of the entire solution in liters. And so whenever we see this capital M, the units that it is telling us would be moles divided by liters. Here's an example of how we can make a solution with a specific concentration, and we'll be doing something like this in an experiment that's coming up. This is called a volumetric flask, and it is specifically designed to hold a particular volume and measure that precisely and accurately. So here we're going to make a 1 molar sodium chloride solution, meaning there's 1 mole of sodium chloride per liter of solution. So we weigh out 1 mole of sodium chloride and we put it into the flask. It can be it's often easier said than done, but they're just pouring it in. So 1 mole of sodium chloride would be 58.44 grams. Then we're going to add some water. We're not going to fill it all the way up initially. We're going to fill it partway up the shoulder here, and we're going to swish it around and mix it until all of this solid dissolves. Because when the liquid level is down here, you can still shake it around and mix it real easily. Once you get it all dissolved, then you're going to keep adding water up to the 1 liter mark on the neck of the flask. You want the bottom of the meniscus there. And then you're going to put a stopper in it, and you're going to turn it upside down and right side up multiple times to make sure that it gets mixed thoroughly. So if we're trying to make 3 liters of a 2 molar solution, how many moles of solute would we need? So when we see this 2 capital M, that means 2.0 moles per liter. Right, 6. We want 3 liters, and there's 2 moles in each liter, so we need 6 moles. Any questions? What we'll see very soon is that molarity is a very nice conversion factor between moles of solute and volume of solution. So 3 liters times 2 moles per liter, the liters cancel out and gives us 6 moles. This is a conceptual problem, so we're supposed to just do that in our heads, but any questions? So here's one with a little more calculating. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So the first step is always to read through the problem, and then we want to identify the information that's given. So that's usually things with numbers. 45.4 grams of sodium nitrate and 2.50 liters. That's the information we're given. And what are we trying to find? The molarity. So what does molarity mean? Moles per liter. So molarity equals moles of solute per liter of solution. Do we know either of those numbers?
We know the amount of liters.
Yeah, we have the liters of solution, so this is the volume of solution. But they don't give us the moles of sodium nitrate,
So we're gonna have to find it.
so we have to find it.
We have the amount of grams, so keep
Yeah, so what we're going to do is we're going to take grams of sodium nitrate and change that into moles of sodium nitrate.
just one for
So 45.4 grams of sodium nitrate. We want to find moles, and so we're going to divide by grams, get our units in there, and then the relationship between moles and grams is the molar mass of the compound. So we have the formula, we have the periodic table, and so we'll just jot down here. So sodium is 22.99, and there's 1 nitrogen, 14.01, and there's 3 oxygens, those are each 16. Get out the calculator. My calculator says 85. Is that the right number of sig figs?
We had 0, 0.
We need to add some zeros. The calculator doesn't understand sig figs. When we do molar masses and we've got 4 sig figs for all the atomic masses, then we should have 4 significant figures in our result, and so we need to outsmart our calculator. So 1 mole of sodium nitrate weighs 85.00 grams. So 45.4 divided by 85, 0.534 0.12 moles. We started with 3 significant figures in our mass. This should have 3 significant figures. I'm not done calculating, so I'm going to keep the next 2 digits. So here we have our moles of solute. So we can now plug these into the equation. 0.53412 moles divided by 2.50 liters. So 0.21365 moles per liter. Rounding that will give us 0.214. And then we often use that capital M as the abbreviation for moles per liter. Any questions?
Second.
So the molarity of a solution is a conversion factor, just like the molar mass of a compound is a conversion factor. Molar mass converts between moles and grams. Molarity converts between moles and liters of solution. So here, if we have a 0.500 molar sodium chloride solution, that means there's 0.500 moles of sodium chloride for every 1 liter of solution. 0.5 moles sodium chloride per liter. So using it this way, we can convert from liters of solution to moles of sodium chloride. If we turn it upside down, we can convert from moles of sodium chloride to liters of solution. I think the thing that trips up students the most is you see that capital M and you write it down as a capital M and your brain isn't processing that that's moles divided by liters.
So it's best just to write it out.
It's best just to always write it out moles per liters. So, they give you something like this in a problem and then you're going to write it down because that's what we do. We write down the numbers. We should write that down as 0.500 moles per liter. Then our brain says, oh, that's moles per liter. So how many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? Well, they're giving us some information. We've got a volume of 1.55 liters, and we've got a concentration, a molarity here. And then what are we trying to find?
Grams of sucrose.
Grams of sucrose. So molarity is to be used as a conversion factor. So I'm going to take my numbers and I'm going to write them down. I have 1.55 liters and I have 0.758. And instead of writing capital M, I'm going to write moles per liter. And you might as well just make that line go all the way across. Moles per liter. Anytime you have units with the word per in them, that's probably going to be used as a conversion factor. So here we're given 2 numbers to start with, and we need to come up with grams of sucrose. So this is dimensional analysis. We need to figure out how are we going to get from these numbers to grams of sucrose. Well, we have to choose which one we're going to start with, and almost always we're going to start with the one that does not have per units. So we're going to start with this volume. And this will be used as a conversion factor. This allows us to convert from liters to what? To moles. So I can go from liters to moles, and then we've already learned how to convert from moles to grams using molar masses, right? So I have 1.55 liters. There's 2 arrows in my path here. So there's 2 fractions in my equation. Liters is going to be down here. Moles is going to be down there. The relationship between moles and liters was given. That's the molarity. 0.758 is with the unit mole. Mole's on top, so I'm going to put this number on top. And that's per 1 liter. You can write the 1 down there if it makes you feel better. Grams per mole. We need the molar mass. They gave us the formula because we don't expect you to know the formula for sucrose. So there's 12 carbons. And there are 22 hydrogens. And 11 oxygens. 12 times 12.01 plus 22 times 1.00h, 8. Plus 11 times 16. What? It is a big number. Sucrose is a large molecule. There are actually molecules that are much, much, much larger than that, called proteins.
And if getting started on DNA.
Yeah, we're not gonna talk about DNA. A DNA molecule is so large that you can actually see it.
Yeah, I know. What is the saying? It's so long that you can go to the moon and back with it 3 times over or something like that.
I'm not sure about that. But if you separate DNA out of like a strawberry or something, you can lift it out of the solution and you can actually see it. Right? Yeah. Okay, so that's the relationship between grams and moles for this compound, right? It would be this many grams for 1 mole of the compound. So I'm going to put this number in here, 342.296. And then I'm going to get out my calculator again, 1.55 times 0.758 times 342.296. Again, as is often the case, my first number had 3 significant figures, my molarity had 3 significant figures, so my answer is going to end up with 3 significant figures. And the unit left there is grams. So we would report that there are 402 grams of sucrose in 1.55 liters of 0.758 molar sucrose.
I kind of want to see that now.
Oh, the DNA?
Yeah. Is there a theoretical limit on how big a molecule can get?
Not that I know of.
I'm scared.
Any questions? These types of calculations are really, really important. Okay, stoichiometry, conversions with molar mass, conversions with molarity, these are things that show up all the time in chemistry. So these are ones we really need to get down pat. Okay, let's think about this one. If we dissolve 25 grams of salt in 251 grams of water, how much is that solution going to weigh? This is not exactly related to anything we've been talking about, is it? Well, what does common sense say? You just add them together, right? Yeah, that's the answer. 251 plus 25, if my brain's working correctly, that's 276. Conservation of mass. When you put two things together, their mass doesn't change, right? The kind of trippy thing is sometimes their volume changes, but the mass is not going to change. We often store solutions in a more concentrated form. We call these stock solutions. We store them in the stock room. And this is a little bit like getting those concentrated cleaners from the store, right, and keeping them in the cupboard. And when you run out of cleaner in the spray bottle, you pour a little bit of the concentrated stuff in there, and then you add water and dilute it, right? And that saves on the shipping of water back and forth, uses less plastic bottles to contain the stuff, and it's more convenient, right? So we do this in chemistry too. So to make lower concentration solutions, we add more solvent. When we do this, the amount of solute doesn't change. Only the volume of the solution is changing. So the moles of solute that we have in the original solution will be equal to the moles of solute in the second solution. What's different is that the volume is larger. Those moles are more spread out, but they're all still there. So we find that the concentration and volume of the stock and diluted solutions are inversely proportional. The concentration, molarity, moles per liter, times the volume of the first solution would give us the number of moles in the first solution. Molarity, moles per liter, times volume in liters of the second solution gives us the moles of the second solution. The moles of the first solution is equal to the moles of the second solution. So if you think about the orange juice again. So you got your can of frozen concentrated orange juice, and you've got your big pitcher, and you squeeze all that stuff into the pitcher, and you've got like this orange goodness, right? And then you start adding water to it. Does some of that orange goodness disappear? No, it's all still there. It's just getting spread out among the water, right? The orange goodness is all still there. We're just changing the volume. How do they make concentrated orange juice? They take orange juice and they take the water out of it, right? So that it takes up less space and you can keep it in your freezer. It's more convenient. Any questions? So here is an example of diluting a solution. So we're making 3 liters of a 0.5 molar solution from a 10 molar solution. So here we're measuring 0.15 liters of 10 molar solution. Oops, not what I wanted to do. So if we have 0.150 liters of a 10 molar solution, that's 10 moles per liter, that's going to mean we have 1.50 moles of the solute, right? So we're going to put that into this flask, and then we're going to add water until the volume of the entire solution is at 3 liters. So over here, we still have our 1.50 moles of the solute. We put it in there, it didn't go anywhere. We're adding water so the volume changes. The new volume is 3 liters. And so the new concentration, I should be able to do that in my head, but I don't dare, is going to be 0.500 moles per liter. This is the equation that we can use for dilution equations. M1V1 equals M2V2. This is the molarity of the first solution times its volume. That's going to equal the molarity of the second solution times its volume. If we're trying to find the new molarity, we can just rearrange this equation. So if I divide by V2, those cancel out. And that is equal to the molarity of the new solution. And that's what I did in this calculation. Here's the molarity times the volume, and I took that result and I divided it by the new volume. That gets me the new concentration. Questions? So to what volume in milliliters should you dilute 100.0 milliliters of 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? You can do this using a variation of dimensional analysis. Most students prefer to use the equation, and that is absolutely fine. So that's what we're going to do. So we have 100 milliliters, we have 5 molar, and we have 0.75 molar. The important thing here is that we are diluting. There's no chemical reaction going on. Students like this equation so much that they try to use it in places where it's not appropriate. So this is just when we're diluting things. And we're trying to find the volume. So the equation is molarity 1 times volume 1 is equal to molarity 2 times volume 2. In some books they say MC, VC, and MD, VD for dilute and concentrated. You can do it that way. What's important is that you get them matched up in the right way. So do you see how 100 milliliters of this, those are together, right? So let's put a box around those. Those two numbers go together. There's a volume and a molarity. Well, let's call this one V1 and this one M1. So that's V1, this is M1. Then I've got another molarity. Well, there's molarity 1 and there's molarity 2. So this one must be molarity 2. And they're asking me what volume? That's going to be volume 2. So this is saying, what's the volume of this 0.75 molar solution? It has 100 milliliters of 5 molar calcium chloride in it. So I'm searching for volume 2, so I can rearrange my equation here. Volume 2 is equal to M1 V1 divided by M2. And then we can put the numbers in. So molarity 1 was 5 moles per liter. And volume 1 is 100 milliliters. Now, if that's all we were going to do, we'd have a little problem with units, right? But let's just hold off on the units for a minute and see what happens. In the denominator, I have molarity 2. That's this one, 0.750 moles per liter. If we look at the units over here, what happens to the moles per liter? They're going to cancel out. Moles cancel moles, liters cancels liters, and the unit that's left is milliliters, which conveniently is what they're asking us for. Now, you could change this into liters, do the problem, get the answer in liters, and change it back into milliliters, but that's more work. So here, the answer then would be 5 times 100 divided by 0.75. So that's going to give us 666.6 repeating milliliters. How many significant figures should we report the answer to? 3. This one's got 4, but this one's 3 and that one's 3. So taking this to so we avoid the 666 just barely because it rounds up to 667. And then we should always check and make sure that our answer is making sense. So we're talking about taking 100 mils of this and adding water to it, diluting it. Is that going to make the volume get bigger or smaller? Bigger. The volume's going to get bigger because we're adding water. So the volume that we end up with is larger than we started with, and so that's very encouraging that we probably did it correct. If this ends up being smaller, you've got something upside down, because you can't take, say, that the orange concentrate and add water to it and make it smaller, right? It doesn't work like that. Any questions?